Hello, I'm Diana Marin, and I recently defended my PhD at TU Wien, titled Proximity-Based Point Cloud Reconstruction. My work poses a deceptively simple question. Given disconnected samples, how can we connect them such that geometry and structure reemerge? The usual answers include the nearest neighbor graph, the minimum spanning tree, the relative neighborhood graph, the Gabriel graph, or the Delaunay triangulation. An outlier of this hierarchy, and the connecting thread of my thesis, was the spheres of influence graph, or SIG. First introduced by Toussaint, two points are connected in SIG if the distance between them is smaller than the sum of their nearest neighbors. Visually, this can be interpreted as centering a sphere at each point and growing it until it touches the nearest vertex. Then, we connect all points whose spheres intersect. In other words, SIG encodes local density without a fixed parameter. We investigated the properties of this graph and its extensions in various contexts: curve reconstruction, clustering, and data analysis. For curve reconstruction, we intersected the Delaunay triangulation, which provides clean geometry, with the spheres of influence graph that provides local density to obtain the SIG-DT. We proved that this graph contains the correct reconstruction under sparser constraints than state-of-the-art. With additional inflate and sculpt post-processing steps, we are able to reconstruct manifold curves in more cases than prior work. Once the curves are lifted to non-planar surfaces, and more generally to Riemannian manifolds, we also adapt our curve reconstruction method. We transform the SIG-DT into SIG-DV by exchanging the Delaunay triangulation for the dual Voronoi graph. We extend our theory and method to these spaces, and both analyses and experiments show that we can reconstruct with far fewer samples, reliably recovering multiple curves directly on non-planar domains. Lastly, we introduce a new proximity graph, the Stability Incorporated Neighborhood Graph, or SING. By extending the spheres of influence graph to a more flexible definition, we obtain a noise-robust structure that takes local density into account. This allows us to use topological data analysis to find meaningful clusters, while only requiring a distance semi-metric defined on the given data. From SIG-DT for curves in the plane, to SIG-DV on manifolds, to SING for clustering, the path is the same. Encode proximity well and structure follows. Through my thesis, I've shown that a seemingly small modeling choice, namely how we define proximity, scales to a big and provable impact. Thank you.